Okay, Dr. Matthew J. Trom here. This is the next fluids refresher video, and in this one I'm going to share with you the definition of viscosity and how to derive it, and how to get to the final equation for viscosity. Just as a reminder, this is the list of all the things that I think a mechanical or aerospace engineering student should know once they've survived a fluids class. And as you can see, the definition of viscosity is the number one thing on the list. So it's pretty important. This is fundamental to mechanical and aerospace engineering fluids. Okay, let's jump right in. Viscosity, I'm going to give you two definitions. The first is kind of the pure thermodynamic definition. So viscosity is a thermodynamic property of fluids that equates the fluid strain rate to the applied shear stress. Now, I'm going to highlight this to emphasize it. We're equating the fluid strain rate to the applied shear stress. That's what viscosity is doing. So we're going to, in the next slide, use that combination of words to develop an equation to tell us how to handle viscosity mathematically. But I also want you to get kind of just a physical intuition for what viscosity actually is, what it feels like. And so in more tangible terms, viscosity is a fluid's resistance to flow. So it's the thickness or the laziness of a fluid where you're trying to induce the flow of the fluid. Viscosity is sort of the resistance to that flow. And to give you a sense of what this looks like, I have this YouTube video here. So the container on the left is filled with a low viscosity fluid, and the one on the right is a high viscosity fluid. Now, I could watch this, of course, over and over and over again because I'm a thermal fluids guy and I love this stuff. But I promise I'll only make you guys watch it like 2 or 3 times. Okay, so let's run the video, and you can see the fellow shaking the fluid on the left, low viscosity fluid, high viscosity fluid, and now he's going to pour the low viscosity fluid, which probably is liquid water. So you can see it just very nicely flows and fills up the container. Here's the high viscosity fluid, probably corn syrup, maybe glycerol. It flows very, very slowly, right? So it's resisting the force of gravity, pulling it out of the top beaker into the bottom beaker, and flows very, very, very slowly, resisting that force because it's thick, it's lazy as a result of having high viscosity. Okay, let's watch it one more time. Okay, so you can see the surface waves there, big surface waves for the low viscosity fluid. High viscosity fluid, very few surface waves because it's resisting the force of this fellow shaking it. Here's the low viscosity fluid pouring, very quickly fills up the container. Here's the high viscosity fluid. You'll see it forms this almost pyramid shaped column. So you can see it there, just this pyramid shaped column as it's resisting the force of gravity, flowing out so slowly because it has such a high viscosity. So super cool. I love watching that stuff. Okay. Anyway, hopefully that gives you a physical sense of what viscosity actually means. Again, it's the thickness or the laziness of the fluid. It's its ability to resist a force or a pressure that's causing it to flow. Okay. Now let's jump into the formal mathematical definition and where it comes from. So recall again that viscosity effectively equates the strain rate of a fluid to its applied shear stress. So the way to think about this is to think of just a particle of fluid, and my particle is a square. So it has a length of delta x, it has a height of delta y, and then it has some distance into the page, which we're not going to worry about. This fluid is basically being sheared on the top and the bottom, right? So on the top, the shear is going to the right, and on the bottom, the shear is going to the left. Now, what differentiates a fluid from a solid is how it responds to a shear. So a solid, if you sheared it like this, would deform, it would strain to some extent, but eventually it would stop, right? So that's what differentiates a solid from a fluid, where if you put a shear on a fluid, it's just going to continue straining and deforming basically forever, right? So it just continues and continues to strain. So really what kind of defines a fluid is not how much it strains, because it'll strain forever. It's the rate at which it strains, the strain rate. And so that strain rate is represented essentially by the velocity that the top of this fluid moves as it's being sheared. And if I multiply that velocity, which we'll call delta U, by some amount of time, which we'll call delta T. These are all, of course, differential terms because what's going on here is happening at a very small scale. That velocity times time is a distance that this fluid particle is shearing. And again, the height of the fluid particle is delta Y. And the height of that particle and the distance that it's shearing, well, those happen at right angles, and so that forms this nice right triangle. And so really, the rate of strain of the fluid can be thought of as this delta theta, this angle that gets formed as this previously square or cubic shaped particle of fluid starts to strain, starts to deform under this shear stress. So we're just going to take advantage of the fact that there's a right triangle here, and we are going to use some trigonometry to sort out the equation. So now remember, viscosity equates strain rate of the fluid to the applied shear stress, right? So tau here is the applied shear stress, and the strain rate is the rate at which this angle is changing, right? The rate at which this angle is growing. So delta theta divided by delta t. So we don't yet have viscosity in this equation, but this equation here, tau being proportional to delta theta over delta t, is going to become important in the next slide. Okay, so let's get back to this right triangle. I'm going to just use some trigonometry, so I'm going to remember that the tangent of an angle is the opposite over the adjacent sides of a right triangle, and I'm going to just write that down here. So tangent of delta theta is equal to the length of the opposite side divided by the length of the adjacent side. Okay, and I'm now going to invoke a small angle formula. So remember, for relatively small angles, and everything here is small, right? These are all deltas. They're infinitesimally small changes. For a very small angle, tangent of a small angle is equal to sine of a small angle, if you remember that from your math courses. And sine of a small angle is just the angle itself, right? So this tangent delta theta is effectively just theta for relatively small angles, which is what's happening here because these are differentials. And so what I end up with is basically delta theta is equal to delta U times delta T divided by delta Y. I'm just going to take the delta T, divide both sides by that, and I come up with this equation here. Delta theta delta T, or d theta dt, is equal to du dy. And this is important because remember, we now up here have this relationship that relates the shear stress on the fluid to the rate of strain, and here I'm using that rate of strain to describe basically an internal velocity profile. So we'll see this on the next slide a little bit better. Okay, so here's that same equation from before, right? So I'm just taking this guy and I'm copying it here. And this is the previous equation from before, right up here. And I'm just going to put them together, and I'm going to substitute this d theta dt in here, and what I end up with is that tau, which again is the shear stress, is equal to now this constant of proportionality, right? That's what this symbol means, is that tau is somehow proportional to d theta dt, so the constant of proportionality multiplied by du dy. So it's just that simple. And this equation here, that's the equation for viscosity, because that constant of proportionality, mu, that's viscosity. So again, remember, viscosity just equates strain rate of the fluid to applied shear stress. That is literally what this equation is telling us, because we've taken this square or cube of fluid and we've actually looked at the strain rate, and we've got an expression for the strain rate, and we've been able to plug it into an expression for the shear stress to come up with this expression. Okay, so du dy, what is that? Well, it's a velocity profile. So du is a velocity, and dy, or u, is a velocity, and y is some distance from the origin. And so we'll see in follow-on examples how to use the shape of the velocity profile to work out through the viscosity equation the shear on surfaces over which the fluid is flowing. Okay, so that's all I want to say about the definition of viscosity. We will use this again in subsequent refresher videos, but for now, you guys are up to speed on this particular concept within fluids. So look forward to seeing you in the next video. Thanks for your time. Bye.